This is a demo of the logical operations in a single cycle computer. I've opened viciLab and I'm going to open up the SEC Inv And Or Xor, a VLA viciLab application file which demonstrates the behavior of those instructions. So enter your username and viciLogic password and it will configure an FPGA. The IDE appears with lots of tabs: invert, or, exclusive or, and there's a few other instructions here as well in the program which demonstrates the behavior. Open up the individual instructions folder and open up the corresponding Inv And Or Xor assembler language. You can see there are some registers being set up here, R4 and R1, and then the AND, the OR and the XOR are included, and the INV instruction is used at the top. Assemble the program, transfer to program memory, and you can see that the AND or XOR INV view tab is on the right hand side, and here are the instructions. So the first instruction is INV R4 to R4. So in the instruction we have the 7-bit opcode. R4 is the source address, RIA, and the destination address. RIA is here, it selects register, fed back through this multiplexer in the operand fetch, register 4, through the function execution unit in which the logical behavior is illustrated here in the tab and no other, and the active path is the INV path, the inverter path, because ALU function in the instruction decoder and cell logic, those 3 bits are all assertive. And this multiplexer is within the function execution unit, which when select logic is asserted, selects the logic element out as opposed to the arithmetic or the bit handling or the shift or rotate, which are in other instructions. The data and stack has not been used, and you can see that the 0 coming in from the register down here, register 4, is inverted through this to give FFFF and through it into the write back function. The red illustrates here that the register bank R has been written to index 4 given by the destination register, and reg write signal is inserted in the instruction decoder to make that write happen. And as is quite normal, the program counter is incrementing on the next clock edge. So these 3 bits are not used at all in the instruction, and this is the instruction 3720, which is over here at program counter of 0. So if I step, register 4 will go to FFFF. The view will change in the tab because now a clear bit is being used. There's a few instructions in the program to put a particular pattern in R4 and R1, so I'm going to single step through those because they're not necessary for part of this demo. Now I'm at the AND instruction, and the AND here has an opcode different from the INV. The output is register 7. There are 2 inputs, register 4 and register 1. Register 4 selects R4 through here. Currently R4 was defined as FFF3. After the invert there were 2 clear functions, and it's being ANDed with R1, which is a value 0208 in it, and they're going through this path. The star illustrates that. ALU function, both bits are now deasserted for this particular instruction. The destination is register 7 and register write is asserted. So if I AND 0208 with FFF3, it gives out 0200. And this is written to register 7. The program counter will increment and step. Now there's an OR function. Again, 4 and 1. Again, the same values as before. Now I'm ORing 0208 and FFF3, and the result is FFFB. And it's written again now to register 7, which is currently 200. And it will now go to FFFB. And the last is the exclusive OR, which exclusive ORs FFF3 with 0208, and the output is FDFB. So single step one more time, and this is the result. And then the end instruction view appears, in which the end signal in the instruction decoder is asserted, and that forces the program counter to stay unchanged no matter how many clock cycles occur. The opcode is all zeros, and the other fields in the instruction are not used, and no activity in terms of to from data memory, stack memory, or registers occurs. There's no connections here to illustrate that. That's the end of the demo. I'll continue now with a more in-depth analysis of the tabs on the right hand side. So I reset the program. Program counter goes to 0. I'm back at the invert instruction, and I can, if I wish, select the full features of the hardware operand fetch, function execution unit, and write back here. So I'll go first to the operand fetch, and this shows all of the details of the operand fetch. So in this case, all the registers are 0. I'm bringing in register 4, and it's being selected by RIA, which takes R4 through here and gives the value out 0. So this is the data that's coming through the operand fetch. The rest don't matter because they're not being used. B isn't being used, and special function register is not being selected through this multiplexer because all of these other signals are deasserted in the instruction decoder. So now I'm going to go to the function execution unit, which has the logic block, which is where I am now, the arithmetic, which is not being used at the moment, but doing something, but not selected. The logic unit output is being selected through this mux that I showed previously, and the output is FFFF. The shift and rotate again is not being selected. The path through to the output is here. All of these, while performing some task, are not actually being seen in F unit out signal, and this set clear invert bit is the same. A and B are both zeros. A is the parameter that's being used. B signals are not being used here. ALU function and cell logic are asserted. So now I will look inside the logic unit, and the logic unit has A coming through. In fact, there's an issue in this drawing. The input to the inverter should actually be from A, from this path connected across to there. So I'll update that picture in the released images. It's selecting with ALU function both ones, path 3, FFFF is the result, and again out through select logic. So I can go back to function execution unit, and then into write back, which takes the result FFFF through here. Look at the blue stars, all of the active data path through to the register. So this detail has not been shown yet, but it's the default data path from F unit out to the register bank. And in this particular case, register write is being asserted, and it's going into this block and that block, and it asserts an internal signal in the HDL models, write reg R, which causes a write to the register bank rather than the SFR bank, and to register 4 R0 address is 100, and the data coming through the multiplexers is FFFF. Inside this block are special function registers which have timers and stack pointer, etc., and all of these. I'll now go to the program counter control unit, and you'll see that currently the program counter is 0, and it's coming through the default path being the increment path through here and through here. So we see that the next state is 1, so when the clock is stepped, this will move through and the program counter will go to 1. And now I'm in the instruction clear BR, etc., because it's putting the patterns FFF3 in register 4 and 0208 in register 1, so that they will be operated on AB for ANDs, ORs, and XORs later on, as was shown in the earlier demo. So I'm going to single step and get to the AND function, and this time again go to the operand fetch. Now I have two values coming through. One is R1 and R4. R1 is the value from 0208, which is coming out on the B bus. R4 is FFF3, and this is here on the A bus. And RIA selects this path. RIB, which is 001, selects this path. All the other signals are deasserted. I go to the function execution block, and in this case now, again, this unit is the one of interest. And in this case now I'm doing an AND. Both A and B are going to AND. This path is selecting the results. So I'm ANDing all of these bits with all of those bits. And the only one which has two ones, a 1 in this and a 1 in that, will give the result out. And the only one is bit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Bit 9 is asserted in this, and that's all. You'll see bit 0, 1, 2, 3, it's deasserted here, it's asserted here. So ANDing them will give a 0. There's only one bit that will be asserted in the output, and the output is the value 0200. Step again. Now I'm ORing them. Again, I can go to the function execution unit, into the logic block. Now the OR is happening because ALU function is 01 from the instruction decoder. The paths through the muxes are the same as before, and the answer now is FFFB because I'm ORing. All of these that are asserted will be asserted in the output. But just notice that these two that are deasserted Are any of these asserted? Yes, bit 3 is, so bit 3 in the result is asserted as well, and bit 2 remains 0 because it's 0 in both A and B. Step again, and into XOR. And again going to function execution unit and go into the logical unit. Now I have the XOR path, and anywhere where they are different, we will have a 1 out. So all of these 6 zeros and these 6 1s, we will get 6 1s out. This bit is a 1, this bit is a 1, so they're both the same, so we'll get a 0 out. So where bits differ, there will be a 1 out. Where they're the same, there will be 0 out. So bit 2, which is a 0 and a 0, because they're the same, there will be a 0 out. So the answer is F, D, F, B, and I can step once more to the end instruction. So that elaborates the use of the more detailed view of the signals and the behaviour and all of the functions inside the single cycle computer.